Good morning. Today we're going to see a controller in control system. A controller is a mechanism which minimizes the error between the actual value and desired value of the system. It is a fundamental part of a control engineering used in all complex control system. So it will improve the steady state accuracy by reducing steady state error, and also it improves the stability of the system and improves the transient response of the system. If we can take the closed loop block diagram representation, controller placed between the error detector and plant. So the controller input represented by the error signal E of t, which will be the difference between the reference input and the actual input. And the output represented as a U of t. Controller output will be represented as a U of t. If you analyze the different types of controller, today we're going to see the proportional controller, proportional integral controller, proportional derivative controller, and proportional integral derivative controller. We start with the proportional controller. Name implies there is a proportional controller output signal which is proportional to error signal, and this output U of t is proportional to error signal E of t, with if equating the proportionality constant as a kp. The proportional controller normally amplifies the error signal and increases the loop gain of the system. So this loop gain improves the steady state accuracy and also rejects the disturbance of the signal and improves the relative stability of the system. So drawback is it produces constant steady state error and also decreases the sensitivity of the system. And the main for a proportional controller, there are two conditions. The deviation between input and output should not be very large, and also the deviation should not be sudden one. If you go for the second controller, that is a proportional integral controller. It is a summation of proportional controller and the integral controller. Here, the integral controller can be represented as a integration of error signal E of t with the integral gain non represented as ki, that is represented kp by ti, which is also known as controller gain. This integral controller also known as reset controller. So it has a unique capability that the integral controller can return the control variable back to the exact set point following a disturbance. That's why it's known as a reset controller. Yeah, if you mathematically you can represent as a u of t equal to kp e of t plus kp by ti integral of e of t dt. If we take the Laplace transform, if you find the controller transfer function, u of s by e of s can be represented as a kp into 1 plus 1 by tas. If you analyze this proportional integral controller with in the closed loop transfer function, if you consider the plant as a second order system, that is omega n squared by s into s plus 2 zeta omega n s. If you analyze with the closed loop transfer function, if you find the c of s by r of s, we can finally will be getting this final equation as this one. There is an increase in order here by 1 and also introduce a 0 in the system. And also there is a type number of the open loop system increases by the 1. So this will reduces the steady state error. But increase in 0, what will happen? That increases the peak overshoot. So from this you can conclude from the proportional integral controller, there is steady state error can be reduced, but the peak overshoot will be remains in the system. If we go for the proportional derivative controller, so it is a summation of proportional controller plus derivative controller. Here derivative constant represents as a kp into td, and with the derivative function de of t by dt. So if you take the Laplace transform and if you find the proportional derivative transfer function as a u of s by e of s as kp into 1 plus td into s. Again, if you analyze with the second order system, that is omega n squared by s into s plus 2 zeta omega n, we can find the final transfer function obtained like this. Here there is an increase in 0, normally increases the peak overshoot. But the increase in damping is there, always reduces the peak overshoot. So from this, the proportional derivative controller normally reduces the peak overshoot. But it there will be a steady state error always present in the proportional derivative controller in the system. We go for the proportional integral controller next. So proportional integral derivative controller. So this is a combination of all the three, that is a proportional integral and derivative action. It is clear from the above discussion that suitable combination of proportional value, integral value, and derivative value can improve the all the desired performance of the closed loop system. So, and also this proportional integral derivative we have the widely acceptable for the industrial process since it is a robust one. That's why it is widely used in the industrial application. However, you have to properly choose the proportional integral derivative parameter. That is very important. Unless the parameters are properly chosen, the controller may be leads to the instability of the closed loop system. So if you see the mathematically the proportional integral derivative, the controller transfer function can be represented as Kp into 1 plus 1 by TAS plus TD into S. So proportional controller stabilizes the gain but produces steady state error. But integral controller eliminates the steady state error, but derivative control reduces the peak overshoot of the system. If you analyze this controller in the Matalab simulation, let it be considered the second order system. G of s equal to 10 divided by s square plus 2s plus 4 with unity feedback. You can see the without controller, there will be a peak overshoot is there, as well as will have this steady state error is there. Again, if you can use the proportion derivative controller, if you choose the for the system, we can see that the peak overshoot is completely reduced, but there is a peak steady state error present in the system. If you go with the proportional integral controller for the same transfer function, automatically reduces the steady state error. That is for the step input of 1, the steady state error is completely eliminated here. But the peak overshoot is again present in the proportional integral controller. So if you use the proportional, integral, and derivative controller, so automatically you can see the steady state error is reduced, and also peak overshoot also reduced. So generally, if you use a proportional constant, the rise time is decreases. Mainly rise time decreases. The overshoot also increases. Settling time there will be a small change. Steady state error decreases. But integral constant completely eliminates the steady state error. That there will be increase in overshoot as well as settling time. But rise time decreases. For derivative constant, mainly the overshoot decreases. Settling time also decreases. So rise time small change will be there. Steady state there is no change in the steady state error. Thank you.